Welcome back to CSAI Think Tinker Learn. This is part of my System Design Essential series. The goal here is to give you a solid mental model of system design topics. We are breaking down transactions and isolation levels today. This is a concept first introduction to help you build your system design foundations quickly. If you want to see a deep dive on the trade offs or a specific case study, let me know in the comments. Before we begin, if you like this video, please do consider hitting that like button, sharing this video, and subscribing to this channel. This series is designed at a high level to provide a general framework in a very short time. You can find the full technical articles and on my companion site. The link will be in the description. Now, let's pull apart the engine that keeps your data from destroying itself. Okay, the transaction is an atomic unit of a database. And in a healthy system, there is absolutely no middle ground. Your operation within a begin and a commit block either succeeds completely or is rolled back as if it never started. If the pipeline breaks halfway through, we erase everything. There's no such thing as a half-saved state in a production-grade database. It is a binary reality. Either the whole world payload is permanent or none of it is. The reliability of this system rests on four load-bearing pillars of asset. Atomicity ensures all or nothing execution, usually backed by a write-ahead log or wall. Consistency ensures business and schema rules are never violated. Durability guarantees that once a commit happens, it's flushed to the physical disk. But isolation is a troublemaker. Perfect isolation means serving one user at a time, which destroys performance. To scale, we have to pull this pillar apart and find a compromise. This is the concurrency bottleneck. 2.1 shows serialized transactions, safe and predictable, but agonizingly slow. In production, we need Tube 2, concurrent execution. We want thousands of users interacting with the data at once to achieve high throughput. However, concurrency breeds anomalies. When two people try to change the same data at the exact same millisecond, data collides. Let's look at exactly how these collisions manifest as bugs. Anomaly 1 is the dirty read. This happens when a transaction A reads data that was modified by transaction B but hasn't been committed yet. If transaction B then rolls back, transaction A is now making system decisions based on ghost data that technically never existed. A real world analogy is reading someone's draft email before they hit delete. If you are acting on information that was never meant to be official. Anomaly 2 is the non-repeatable read, also known as the rug pull. Imagine transaction A reads a row and gets $100. While still doing math, transaction B commits an update changing that row to $150. If transaction A reads the same row again, it gets a different value. The ground shifted while the query was still running. This is a nightmare for aggregate reports where the numbers need to stay static throughout the calculation. Anomaly 3 is the phantom read. While a non-repeatable read mutates a single row, a phantom read mutates a set. Imagine you query for everyone over age 25. While you are processing that list, transaction B inserts a new user who is 30. If you run the query again, a phantom row appears that wasn't there before. It's the difference between someone painting a chair blue, which is a row mutation, and someone adding three new chairs to the room, which is a set mutation. To protect against these, we use the armor, the isolation dial. SQL defines four standard levels. Think of it as a dial rather than a switch. Turning the dial up increases safety and protection against anomalies, but it decreases throughput. Turning it down increases concurrent speed but risks data corruption. There's no best setting. As an architect, you are constantly trading speed for correctness based on your specific use case. Levels 1 and 2 are the Wild West and the practical default level. Level 1 reads uncommitted, allows everything to flow through, including dirty reads. It's used only for approximate analytics. Level 2 read committed is the default for PostgreSQL and Oracle. It ensures you only see committed data, which prevents dirty reads, but your system is still vulnerable to rug pulls and phantoms. It is a sweet spot for most e-commerce and social applications. Level 3 is the repeatable read. This level guarantees that if you read a row once, every subsequent read in that transaction will return the same value, regardless of what other users are committing in the background. It achieves this by taking a snapshot of the data at the moment the transaction begins. This is the default for MySQL InnoDB engine and is perfect for maintaining consistency in financial reporting. Level 4 is serializable, the Iron Fist. Here, the database behaves as if transactions run strictly one after the other. It prevents all anomalies, but there is a massive catch. The database will aggressively kill conflicting transactions to protect the data integrity. If you use this, your application code must include retry loops. You're trading a lot of performance for absolute mathematical correctness. The anomaly shield matrix summarizes the protection levels. Read uncommitted protects against nothing. Read committed shields you from dirty reads. Repeatable reads add protection against non-repeatable reads. Finally, serializable protects against all three, including phantoms. Every step up this matrix provide another layer of safety netting, but make the ascent heavier and slower for the overall system. Under the hood, how do we actually do this? Legacy systems use locks, train A versus train B, which creates massive deadlock risk. Modern systems like MVCC, which is Multi-Version Concurrency Control, think of this as looking through glass panes. Instead of blocking a writer, a database creates a new version of the row. Readers don't block writers, and writers don't block readers. We trade storage space for concurrency, and a background process cleanups the old versions later on. Even with these levels, there is a hidden trap: lost updates. This happens in read, modify, write cycles. If two transactions reads $100 and both try to add $20, the second might overwrite the first, and you lose $20. Interviewers love this because it happens even in repeatable read level. The fix is select for update, which surgically locks that specific row while you do the math, ensuring no one else can modify it until you are done. To wrap up our architecture blueprint, isolation is a dial, not a switch. For social feeds, use read committed for speed. For financial report, use repeatable read. For banking or bookings, the serializable. Now, a question for you. Have you ever encountered a lost update bug in production? And did you resolve it with an isolation level change or a manual rollout? Let me know in the comments. If this helped you, please like, share, and subscribe. Visit the site for more essential. Until next time.